So we're going to go over a couple of things that you guys are asking about. Venn diagrams, flow proofs, logic chains, biconditionals, proof of the angle overlap theorem, and making valid conclusions. Let's start with making valid conclusions. And the cornerstone of this is what I call the hamburger analogy. Make sure that's visual. Okay. So if I say if P then Q, what do we call that? Good, the conditional. And if I swap it so that now it's Q implies P, what's that? Converse. And what's the inverse? If you don't know these, you need to know these. This is like the cornerstone of this unit. What's the last one? Contrapositive. And that's not Q, implies not P. And then you'll remember that although each of these is a form of the conditional, when we think about the hamburger, we have a better understanding of how they're related. These two buns share the same conclusion, so they are reliable. In other words, if I know that this statement is true, this statement must be true. But what about these things in the middle? What do we call these? Oh, maybe that's not the way to spell it. Mystery meat, right? Those things are unreliable. We can't rely upon those. So if I'm given a conditional, for instance, let's say if Zog, then Forzel. Now, again, these are nonsensible words, and I'm using them so that you're not caught up in the context. Instead, you're thinking about the structure. What's my P? Zog. What's my Q? Forzel. So if in addition to this, I tell you, you know what? Last Tuesday, I saw this guy and he was totally Forzel. We don't know what that means, but what I'm telling you is in this conditional environment, Forzel is true. Can you make a conclusion based on that? Here are the steps we go through. Step one, Forzel is our Q. If we're now beginning with this and trying to make a conclusion, I'm asking myself, if Q, then what? Which of our four structures is that? Converse. Oops. Cannot spell today at all. Converse. And is converse one of our reliable buns, or is it one of those unreliable mystery meats? It's a mystery meat. Therefore, I can't depend on it. I don't know that it's going to be P. How can I be certain that I'm not confident? Well, remember that if-then statements can always be written as a Venn or an Euler diagram. And whatever's the hypothesis goes in the small circle, whatever's the conclusion goes in the big circle. And what I'm telling you now is Forzel is true. But I could have Forzel be true here, or Forzel be true here. It's uncertain to me whether it's Zog or not. For this reason, if this were given to me, I'd say no conclusion. Any questions on that piece right there? What if I told you not Zog? I mean, I tried to Zog, but I just couldn't. Can we make a conclusion based on that? If the conclusion were valid, you're right, it would be no Forzel. But let's do it right. Zog is P, so not Zog would be not P, implies something. Which of our structures is not P implies something? Inverse, is that reliable or mystery meat? So that's not reliable. So I have to say no conclusion. Why? Well, if I were to look at my Euler diagram, when I'm not Zog, I could either be here, outside of Zog, but inside Forzel, or outside of Zog and outside of Forzel. It's unclear where I am. Thus, I cannot make a conclusion. What if I were to tell you that this dog came up and he was so cute, he was totally Zog? Can I make a conclusion? Okay, let's do it right. Zog is P. P implies, which structure is that? Conditional. That's what I was told was true, wasn't it? I was told that every time it's P, it's Forzel. Every single time we're in Zog, we're also inside a Forzel. Therefore, I can make a conclusion, and it should be the Q. So my conclusion would be, 3 dots means therefore, Forzel. So we were starting with Forzel, we were starting with not Zog, we were starting with Zog. What's the fourth one? Not Forzel, good. Can I make a conclusion if I were given that if Zog, then Forzel, and not Forzel? Well, that's the Q, and we're doing the opposite of it, not Q. Which structure begins with not Q? Contrapositive, good. Is that reliable or mystery meat? It's reliable. Therefore, what comes after not Q? It leads to not P, which in this case would be not Zog. That's my conclusion. How does that work with the Euler diagram? If I'm outside of Forzel, I'm not Forzel. There's the only place I can be. I can't be inside Forzel. I can't be inside Zog. I have to be outside of Zog. That's why it's reliable. Does that help with making valid conclusions? 5, I've got this nailed. I don't need any more from you on that right now. 3, sort of helps. I'm still a little confused about this. 1, I'm very confused. Okay. Any clarifying questions? Okay, let's do biconditionals while we're talking about it. If I've got a scenario like if 45 degrees, then it's an acute angle. This structure is set up in the conditional. If I were to do the converse and say if it's acute, then it's 45. Are both of these statements true? If it's 45, is it an acute angle? Yes, true. If it's an acute angle, does it have to be 45 degrees? No, it's false. The fact that it's false tells me that if I were to do the inverse, not 45, then not acute, it would also be false because the mystery meats will be the same. You always have 2 patties of the same style. And if I said it's not acute, then it's not 45. If I did the contrapositive, that would also be true. Because again, the burger is always going to have reliable buns. And although the mystery meats are going to be the same, we don't know whether they're true or false. But in the event that I pick something like 90 degrees is a right angle, is that true?
Yes.
Okay, and so then I change it to the other way, the converse, and I say right angle makes it 90 degrees. Is that true? That is true, which means all 4 of them are going to be true, right? Not 90 means it's not a right. That's true. And if it's not right, then it's not a 90. That's also true. So the hamburger still works, right? The bun is reliable. These 2 are the same, and we just can't tell whether they're true or false from the initial statement. But once we test the original conditional and we test the converse, we know that they're all true. When they're all true, I can write it as a valid biconditional because they're interchangeable. So I could write 90, I'd write the hypothesis, I'd leave some space and write right angle. And in between here, I have 3 choices. 1, I could write a double-headed arrow. So I could say 90, double-headed arrow, right angle. That's a biconditional. Secondly, I could say 90 if and only if right angle. Thirdly, I can shorten this and just say 90 what? IFF, right angle. Those are the three ways to write a biconditional. Notice that I've stripped off the if and the then. I'm only looking at the hypothesis and conclusion, and in between is going to be one of the three ways of writing a biconditional. What is a biconditional? It's a scenario where these two things are totally interchangeable. All four of these are true. And if it's a valid biconditional, then I could write it as a definition. A right angle is an angle with a measure equal to 90 degrees. That's the definition. That's what you'd find in the textbook. And the reason I know that is because all four conditions are true, so I can write it as a valid biconditional. Any more questions on biconditionals? Okay. Proof of the angle overlap theorem. So let's call the vertex X, and we're going to say this is S and A and R. Anytime you've got a proof, what you're given to start with is a picture and some information that you're given and some different information that you're trying to prove. No, this isn't the right picture, is it? I need one more piece here. It's okay. All right, now I'm going to get you to understand this theorem first. What does it mean when it's a theorem? What's a theorem? Do you know what a postulate is? It's a rule. It's really obvious. Remember, it's a rule that's so obvious we can just say, well, duh, of course that's true. Theorems are different. It's a rule, but you got to prove it. It's more complicated. Let's say, Ali, would you give me a number for this angle? It doesn't matter what it is. It looks like it's acute. So give me some numerical value for the size of this angle. 35, that's a great choice. And what this theorem starts with is that this angle over here, so the measure of angle SXA, has to be equal to the measure of angle KXR. So that means this is also 35. Now let's see somebody else. Miles, would you please give me how big you think this angle is in here? Sorry, this Miles over here. Go ahead. Yeah. 20 degrees. Totally sounds reasonable. It's a little smaller than the other. Now, if I asked you to tell me about angle SXK, how big is that one? Well, it's 35 for this part and then another 20. So how big is it altogether? 55. And if I asked you to tell me about AXR, how big is that? Also 55, right? We've got 20 and 35. So did I just say that if these measures are the same, then the overlapping are the same? AXR. Do you see the overlapping angles? Here's one angle. And here's the other angle. Do you see how they're overlapping? Yeah, they're overlapping by AXK. That part is like shared for both of them, isn't it? SX. Thank you. You're right, SXK. SXK and AXR. That's right. So I've shown you that if this is 35, since we're told that this is also 35, and then we came up with an angle here, we saw that we could add these together. That's 55 and that's 55. So we proved that this is true. Is that enough to call this a theorem? Will this always work now? Is one example enough to say something always works? No. Should we try it again? Let's make this 36 degrees. And this is 36 degrees. We'll keep this 20. So now this one is 36 plus 20 is 56. And this one is 36 plus 20. It's also 56. It worked again. So is 2 examples enough? 3. How many do we need? How many examples do you think we have to go through before you're 100% convinced that this is true? Isn't this inductive reasoning? Isn't this reasoning from a pattern of evidence and saying that if I see it true a couple of times, I'm going to jump to the conclusion that it's always true? That's not good. So what if we were to do this differently? What if we were to call, instead of numbers, we were to call these variable amounts? Like, let's say that this is A. How big is this angle then? A. And what should we put in here? Good. B sounds good. How big is this angle? Almost. We're multiplying them? A plus B. The numbers are being added together. What about these two? B plus A. Is that the same as A plus B? It is. So now it's more convincing. But if somebody asked me, like, from this picture, why is it true? I don't think it would be clear. So we've got a structure called a 2-column proof to help you model this, to show that it's true. And in our 2-column proofs, what you're always going to find is that we're going to have statements here. And what go over here? Reasons. And on every single 2-column proof, it'll start with the given. So my first statement will be exactly what I said there, that the measure of angle SXA is equal to the measure of angle KXR. What's my reason for that? It was given. Now, the other thing I know is that this has to be my destination. I don't know what number it's going to be, but when I reach the bottom, it's going to have measure of angle SXK equals measure of angle AXR. Can we all buy into what I'm doing here so far? The angles make this a little bit confusing because I have to write out so many letters. So I'm going to start doing this the way we started with the segment addition postulate. Is it the same idea? If I tell you this is 5 and this is 5, no matter what this is, when I add it to both to make the overlapping segments, won't they be the same? So I'm going to redo this now as segments addition because I think it's easier to do. What am I given? Good. AB equals CD. What am I going to try to prove? AC equals BD. And again, I'm doing a 2-column proof. So my statements go here. My reasons go here. What's my first statement going to be? The given. Good. AB equals CD. And my reason is given. And I don't know how far down it is, but what's my last statement going to be? Good. AC equals BD. And I don't know what the reason is here yet. We'll have to find that. I guarantee you it's not the word prove. It'll never be the word prove. So let's think about how we did this with numbers. If I put 5 here and 5 here, and then say I put 7 there, how long is AC? 12. And how long is BD? And the way you did that is you added these up, right? So in other words, we want to take BC and just add it to both parts. We know that these parts stayed the same. So skip a line here. And what I'm trying to get to is that AB plus BC is equal to BC plus CD. Why is that true? How do I get from here to here? Well, the AB is still the same. The equal sign is still the same. CD is still the same. What's changed? Parker? You're adding BC to both sides. What do we call that when you add the same thing to both sides? Addition, prop, equality. Okay. Now, I'm really trying to get to this. This is my goal. Right now, I've got AB plus BC, and I'm trying to get to AC. Does that ring any bells for you? Parker? Beautiful. The segment addition postulate says that AB plus BC equals AC. And so if I know that the left side of this is already AB plus BC, can't I just replace AC for that and put it there? Can I do the same with the right-hand side? What's BC plus CD? BC plus CD is equal to what? BD. That's also the segment addition postulate. And if I take this thing, isn't that the same as this? So I'm going to replace it with this. And then I'm going to take the right side and I'm going to replace it with BD. So take this statement, replace that for that, and that for that with substitution, property of equality, and I reach my end. Now, there is a small, subtle distinction that I'm going to add back in on step 2. What does the addition property of equality say? You can add something to one side of the equation as long as add the same amount to the other. So if I were adding like 7 to this side and 7 to this side, there's no question that I'm adding the same amount. How much did I add to AB? BC. Do we know how much that is?
7.
Well, in my example, it was 7, but really it's a variable amount, isn't it? It changes. So I need to tell everybody that I'm using BC on the left and BC on the right, and they're both the same value. What justifies that step? Good, reflexive. These are the rules we learned last class. You do need to learn them so that you can fill in a proof like this. So let me just go back through this again. I start by saying what I know is true. These two parts are the same. I clarify that this middle thing is the same whether I add it on the left or the right using reflexive. And then I add it up. I say that this one plus this one equals this one plus this one. Just doing it algebraically. I recognize that I've created on the left here AB plus BC, which I know is the same as AC because of the segment addition postulate. And I know on the right, I've got BC plus CD, which I know is equal to BD because of the segment addition postulate. Then if I just substitute AC for the left half and BD for the right half, I get what I was trying to prove. How do I communicate that I'm done? QED. Stands for quad erat demonstratum. Means that which was to be proven. What do you think? 5, I think I could do this proof myself now. 3, I followed you along with it. I didn't get lost, but I'm not sure I could do it myself. 1, I got lost a little bit in the process. I don't actually buy that this is true, let alone could I demonstrate that it's true. Okay. Now, could we do the same thing for the angles? It's the same proof, isn't it? It's just that instead of segments, you're doing angles. So we start with these outer parts are the same. And then we're going to do a reflexive. What's the reflexive going to be? What is it that we're going to be combining on both sides? Good. Hard to see what I have here. AXK, right? So let's say the measure of angle AXK is equal to the measure of angle AXK. So what happens if I add these two together? Measure of XSA plus measure of angle AXK equals these two added together. Why do I get to do that? What's my reason to justify that? Do we all see that this whole equation is still intact down here? We've still got that. We've still got that. We've still got that. What have we brought into the mix? Addition. We did it to both sides, didn't we? So addition, property of equality. You guys ever go to a restaurant when you were a kid and they give you a menu? It's a kid menu. What's on the back of every one of those?
Picture, drawing.
Games of some sort, right? Some drawing, maybe a maze. How do you guarantee that you figure out the path for the maze? Come on, you guys did this too. Start from the end, right? If you start from the end and work your way back, can't you always find the answer to the maze? So let's do the same thing here. We're trying to get to this end space. I want to get SXK. Right now I've got SXA plus AXK. How do I turn those two into this one? Okay, what do you mean by that? Well, that's what we're doing. We're starting from the end by seeing that this is our goal. I need to get this guy in play. I don't have anything up here that says SXK. SXK. What do I know about this whole double angle here? Isn't the measure of angle SXA plus the measure of angle AXK equal to the measure of angle SXK? Right? Isn't this left part A plus this middle part B equal to this whole angle? Remember, we did that when we did protractor work. We saw that we could add those pieces together. And if on the other side it was called the segment addition postulate, what do you think we call it here? That's it. Angle addition postulate. Now we've got SXK in the game. That's what we want, because here's SXK. But we don't have AXR in the game yet. How can we get AXR in the game? AXR. Good. We can say that the measure of angle AXK plus the measure of angle KXR equals measure of angle AXR. Cool. And we can either call that step 4 because it's also angle addition, or we could make it a new step. You have to have a different step for each new rule, but if you use the same rule twice, you could theoretically use the same step. All right, how does that help us? Is this thing the same as this? These are the same, right? So I can replace this with what these two are equal to. which is that. And isn't this the same as this? So I can replace this in place of that. I'm done. This is my sixth step. Angle. No. What did I do? I put this in place of those and put this in place of those. What do I call that? Yeah, substitution. You can take pictures of that if you want. Or in the packet I gave you, you'll notice that near the back, it's got another one of these. And again, for this unit test coming up, I will give you pieces of it and ask you to fill in the missing pieces. I won't ask you to do it from scratch. But there's a little activity here in the end that I think is cool. These two pages are exactly the same, the last and the second to last page. If you want to work more with these proofs and get better with this, what you'll do is you'll take the last page off, and we can use this as a puzzle proof. The way this works is, it's actually two different puzzle proofs. So for instance, you can cut this one off like this. And if you slice first on this dotted line, what you'll have with scissors is this is the beginning part of the proof, and these are all your reasons and statements. Step one is you slice right across here, long strips. And now what you've done is pulled apart all the statements and reasons, and now you mix them up and try to put them back in the right order. If you forget what the order was, remember that the second last page has the same thing in the right order. So you mix them up and put them back in place and make sure that you're comfortable doing that. Once you achieve that skill, you then slice down the middle. And now you've got all these individual blocks. You throw them together, mix them all up, and then try to put them in the right order. And if you struggle, come back and look at this, get them in the right order, mix them up again, do it until you're successful creating this same proof. If you want to really challenge yourself, throw them in a pile, pull out like 4 or 5 randomly, and then try to do it with those 4 or 5 gaps. See if you can figure out what the missing pieces are. This idea of a puzzle proof can be used for both of these versions. They're two slightly different versions of the same proof. All right, 2 more little pieces for today. We're supposed to know about flow proofs. It's very similar to this. This is a 2-column proof. It carries the same information, but it's just a different format. So what I'm going to do is I'm going to zoom this back out a little bit, and I'm going to write this exact same proof in a flow proof format. Here's how it's different. I'm still going to take the first thing as my given, but I'm going to put it in its own little box, and I'm going to hang a little word below it. This is the justification for where it comes from. It was given. Then I'm going to add in my BC equals BC. I needed that because it was reflexive. And again, that comes out of nowhere. It's just true. But then the trick here was, how did I get to this addition property of equality stuff? Well, what I did is I took this information and this information, and I combined them together to say AB plus BC equals BC plus CD. How did I do it? I did it with the addition property of equality. Do you see how it's the same information, but by giving it location and arrows, I convey a little bit more. This came from these 2 facts being pushed together. Now we pulled segment addition out of thin air. It doesn't come from anything. And the other one as well. But the combination of these three is, I'm going to take this expression, and on the right-hand side, I'm going to substitute this. And on the left-hand side, I'm going to substitute this. The result is AC equals BD because of substitution. Substitution. Would you like to take a picture of that? It's the same information presented slightly differently. Who prefers the linear structure of a two-column proof? Raise your hand. Who prefers the graphical structure of a flow proof? Raise your hand. Okay. Some of you refusing to prefer either of them. So what we'll be doing in general in this class is I'll be teaching you both formats, making sure you're comfortable doing both. And then you'll have an option to choose for the second semester about which one you use in general to do your proofs. All right. Looks like the last piece for today is logic chains. If I tell you that, for example, you're going to take the bus from Mill Valley to Marin City, and then we change buses, and you take a bus from Marin City to San Rafael, and then we decide to go from San Rafael to Novato. Overall, we did what? We started in Mill Valley, and we went to where?
Right.
Novato. Right? We started in Mill Valley, went to Marin City, but we changed buses, got on a different one. And then we went to San Rafael, changed buses, got on a different one. And then we went to Novato. So overall, we went from Mill Valley to Novato. It's like a chain, right? This first one is, here's a link, Mill Valley to Marin City. The second one is, here's another link. And then the third one is, here's another link. All we really care about is where the start of the link is and where the end of the link is. The stuff in between is just holding it together. Any questions?